Welcome to a journey towards building a scalable AI serving solution. I'm Moses Guttmann. I'm the founder and CEO of ClearML. Today, we will be discussing how to build your own serving solution that actually scales. We will do it in steps. We'll start small, very naive solutions, and then we'll build on top. Each time, revising, adding more capabilities, analyzing what's working, what's not working, how we can expand and grow. And the idea is that we start with a very small step, meaning the initial MVP should be something that brings value, but also not too much that we can actually implement relatively quickly in order to gain value in actually starting this process of building a serving solution, because this is a journey by all means. So, a bit about myself. I'm a software engineer in my background. In the last 10 years, I did a lot of deep learning and machine learning. Before that, a lot of computer vision. I'm the CEO and founder of ClearML, where we build open source MLOPS solution, starting with experiment management, engineering, automation, orchestration on top of it, scaling efforts in terms of training, and bringing models into production, including obviously serving, as we will be discussing today. So, without further ado, let's dig into what we're actually talking about here. What is a serving solution? We have to first define the requirements for a serving solution. So first, REST API. At the end, the applications need to have something that is simple enough for them to actually use. This means that, generally speaking, metrics representation is just not good enough to actually be used in reality. We want to reduce the technical hurdles for applications to use these models that we're training here. So we have to think simple REST API, not metrics representation of data. Secondly, we have to be very agnostic to the infrastructure. So think Kubernetes, but not tied with a very specific cloud provider or on-prem. It should be agnostic to the type of infrastructure that we have. So it's fine to assume Kubernetes, but what we will be discussing here is a setup that actually scales regardless of your cloud, on-prem combination, whatnot. The third thing is obviously scale. We have to make sure that scale is something that is transparent from our perspective as setting up the infrastructure. So once the infrastructure is set, we want the auto scaling to be as transparent as possible. That means leveraging the capabilities of Kubernetes without us manually having to scale things up, adding servers, etc. So this is dynamic based on the load of the system and not manual, us just bringing more machines into the cluster. Then we have to think about upgradability, not in terms of the service as a service, but in terms of the models. We have to think about the fact that these models are constantly going to change. We are building something here that will allow us at the end to build a CI/CD process for models. So if you're only updating a model once a quarter, every 6 months, then upgrading is not an issue. You can do it manually. But the idea here is to build an infrastructure that allows us to deploy models directly from our Git repositories, really automate this process in a way that will allow us to constantly improve models, because at the end, training the model and actually running it in production, there is a gap here, and we have to understand that this gap will not disappear. We just have to have the infrastructure in order to really streamline this entire process. And lastly is monitoring. So if we think about automation, it's quite obvious that we somehow have to increase the visibility so we know which model is being deployed where, create some insights on how the model is being used by the applications, and lay out the infrastructure for model drift detection, performance detection, degradation, etc. And this is very important when we think about automation. Otherwise, we have zero visibility into this entire process, and debugging becomes a challenge. So let's start with the most simplistic solution. Right off the bat, naive solution is, let's take our code. Let's assume Python code for the sake of this entire talk, because Python that's basically the language is used for training and then for a lot of serving. So let's assume for a second that we have Python code basically repping the model itself. The model itself is running by the libraries themselves, fully optimized on whatever hardware that they're running, and Python is just an easy way to basically do the pre and post processing, right? So we have the Python code wrapped in a Fast API or Flask server, packaged into a container, which we can deploy very quickly on our Kubernetes cluster and have that as an endpoint serving a model. So the upside here, it's very easy to set up. So basically you take your code, you package the entire thing, including the model, the code itself. You have a single container, self-contained, and you can just deploy it, which is terrific. So let's kind of remember here what it means to actually deploy it into our Kubernetes cluster, because we are going to make things a bit more complicated very quickly. So deploying it as basically creating an endpoint, creating a service, testing it internally, curling into the service itself, creating the ingress endpoint, and then deploying it into the production cluster. So this is, and when you think about it from this aspect and this perspective, this is agnostic to the actual Kubernetes service that you're using. So whether you're using Kubernetes as a service on one of the cloud providers or running your own on-prem Kubernetes cluster, it'll be the same process, right? So the idea here, very quickly, we end up with an endpoint running your model. Terrific. Let's think about so it's obvious what we gained, simplicity. What we're losing here is actually granularity and refinement. So the fact that we packaged everything together into a single container actually means that if this model is not being used, meaning no one is firing requests, then whatever resource we allocated for this specific pod is underutilized. It's basically idling. It also means that if this specific model needs a very specific hardware, this hardware is not being shared. So for example, think for a moment on a model that needs a GPU instance. If this model is not constantly being used, then most of the time this GPU instance is sitting idling, and this is not good for us because basically we're paying for it and we do not want to pay for something that is idle. So we have to refine the model, start to think about, okay, so how do we actually separate the two? One portion of this entire thing is still very CPU and very light in terms of compute load, right? The pre-processing and the post-processing, think of them as the way to to create this simple interface on top of the metrics representation of the model. So just fetching data points and then arranging them into an array, or taking back the information and taking a number that represent an index and then returning the result as a text, which is obviously easier from the application level. So this pre and post processing, our CPU, the load on them is not very high, but on the GPU side, that's where the heavy lifting is done in our specific example, right? So in order to do that, we have to separate the process into two. We have to separate into the pre-processing and the inference itself. So the inference itself can be on a GPU, DPU, even very beefy CPU, but it's not the same resource as a pre-processing, and we have to separate in order to have better granularity and then later optimize in terms of cost and scalability, right? So let's revisit the region solution. Let's separate the two. So now we have one container doing the pre and post processing. So the same Flask, Fast API, whatever you want to put there, doing a very simple pre-processing. Basically, this entire process could have been part of the application level, but it should be part of the model, because sometimes it will be changing different models. So think like, for example, the lookup table of the index of the return value from the matrix is different, right? We do not want to burden the application with that knowledge. We want to create a very simple interface for them to use. That's the pre and post processing, right? That's what we have there in the container. We want that container to talk to another container, most probably running on a totally different node, that does the heavy lifting of actually running the model in inference mode, right? And the interface between the two, that's actually quite a generic interface. So if you're using with Kubernetes, KF serving v2, I think, defines a very simple interface. I think this is kind of the default for NVIDIA Triton. Essentially saying, we are passing a matrix. Here's the size of the matrix, number of width, height, number of channels, etc. That's the type. Pass on the data. That's the data that you'll be getting back. Again, define the size of the matrix, the type of data that you'll be getting there, and that's it. That means that this interface is quite generic. That means that the model inference container can be generic as well, and we'll get to that in a second. But from the application level, this is transparent. They still have the simplified interface of REST API accessing it. And in terms of the infrastructure, we separate the two. So now we can start to really think about scale. So we have one node that is doing just basically latency based from the user perspective. That's doing all the work. But in reality, it's passing a lot of the load to another container running on a different pod, running on a different hardware, doing the actual inference heavy lifting. So specifically, we use these capabilities in order to better optimize this entire process. So now, if this is a standalone container, actually multiple processes and nodes can talk to it, it can do the auto batching for us. It can do even the auto scaling. So right now, we have the pre-processing, and the auto scaling with Kubernetes is actually based on, by default, on a CPU load, right? And there's not a lot of load on the pre-processing, but there is a lot of load on the model inference containers, right? So if we set up everything right, the Kubernetes cluster will do the auto scaling on the thing that actually matters, which is the inference, running the model inference. And we have the pre-processing over there, actually better utilizing the original resources that we allocated for it. And that's exactly what we're aiming for here. To use the capabilities of Kubernetes to transparently scale this entire operation in a way that actually makes sense. So scale the parts that actually are doing most of the work. Okay, so revisiting this entire thing. So let's just make sure that we're all on the same page. So we have one container doing the pre and post processing. Think of this container as the container serving a single model, a single endpoint, right? We have to start with a very simple interface. So for example, in this diagram, we have two of them, the main one and the secondary one. Basically, think of them as serving different models, different pre-processing, one container per endpoint. Then we have the serving engine that actually serves both of them, right? It has a generic API, gRPC API, so it's more efficient than REST API because we'll end up passing metrics, maybe more data between the two different pods. And we have the container itself actually serving two models, right? So instead of a container per model, which we might end up with an idle GPU, for example, we have a container actually serving multiple models. And then the limit is actually the memory of that container and not the compute. We let Kubernetes do the auto scaling on the compute while we just limit the number of models in terms of the amount of memory we have per container. So now this container can serve multiple endpoints. And we still have this flexibility of any model connecting with any endpoint, pre-processing, and auto scaling out of the box. So when we think about analyzing this entire process, what do we have to have in this serving engine container in order for actually everything to work out of the box? So, for example, NVIDIA Trend provides it, but also TorchServe and TFServe. What they provide is they're actually a serving engine. So we have to think about it. Serving engine is not the same as a serving service, right? A serving engine, the goal of a serving engine is to do the optimization in terms of model inference, but not as a whole, as a more holistic approach for this entire problem, right? It needs to do the auto batching for us. It needs to be very optimized on different hardwares, so GPU, CPU, TPU, whatever. It needs to be very transparent, so the interface itself should be generic. There is a matrix you have to define, and then you can send data, get it back. It should be as simple as possible. All the rest of the complexity in terms of application should be somewhere else. And obviously, it needs to be able to serve multiple processes or multiple containers, if you will, in a transparent way. So it does the auto batching. So for example, if we have multiple processes sending requests for their different models, we have to make sure that this engine can optimize everything for you. So NVIDIA Trend, for example, does that for you, but also the others. And the idea is that we use them and reason them in a way that Kubernetes can leverage this usage pattern to auto-scaling, right? So if this serving engine container is fully loaded, Kubernetes will create another instance for us, spin it, and then as long as we go through the ingest endpoint, this is transparent from the container's perspective, right? And this is important because we're leveraging the capabilities of Kubernetes together with the capabilities of the serving engine in a way that allows us first the flexibility of pre and post processing, but also the ability to actually build things on top of it in a transparent way so that we do not have to worry about upgrading and creating more nodes when the load increases. And obviously it's the same when the load decreases, right? So we have peak hours, we'll end up with another container of the serving engine. When the load decreases, it will just spin down one of them. We'll end up with a single one, still being able to serve the models as we go along. Okay, so now that we covered a very simple use case of serving models, we have to touch the point on, so how do we actually add more models into the system? And the more naive approach, we had a container per model per endpoint. That means that every time we want to add a new model into the system, we have to first create a container for it. Then it means that we have to somehow tell the serving engine that there is another model weights file. So let's simplify. Let's think of it as a checkpoint or a models file that we somehow have to pass to the serving engine. We also want to make sure that we have some visibility into what's going on. So which models are being served. And we want to have it in a way that does not require us to take down this entire service, right? We want it to be hand over hand. So not every time we deploy a new model, we actually take down the infrastructure for the previous versions of those models. So in order to do that, we have to somehow add another layer of complexity. That means a model repository. Model repository is the place where we put the models. So let's simplify that. Let's think of it as a link to some weights file that sits somewhere on our object storage. But we have to have visibility into what's being used. We have to have some versioning on top of it. So versioning, think of it as we can think of every model as a standalone, but from an application level, it might be another version or a better version doing a better job in predicting or classifying something. And from the application level, it's the same interface. So let's think about it as a version as opposed to just a different standalone. Even though from this, from the design perspective, it might be considered a totally different endpoint. But from the application level, it is important to take into account the application perspective of things, because at the end, these are the users of those models. This is considered just another version of that model. So you have to have a model repository actually keeping track of everything that's being done. From the model serving perspective, we have to think about it from a more holistic approach. So let's analyze what we have here. So we have the ingress, so that's kind of our external endpoint. Then we have a pre and post processing, again, as we had before. And now we have the serving engine container, right? That container now needs to be able to take new models, get them locally, because at the end it needs to serve them. It means that it needs to load them. It means that they have to have it has to have the models inside the container itself so they can be loaded. Then we have the model provisioning sidecar. That's basically the part that will fetch the new models for us when they're being upgraded, put them right into the serving engine container so the serving engine container can actually load them in memory. And obviously it needs to talk to the serving engine container, making sure that it loaded the new models or unloaded previous version, etc. So that version model provisioning container needs to talk to the model repository, meaning getting information on new models being deployed, maybe check if old models need to be unloaded from the system, and fetching the models from the storage solution itself. So in most cases, it'll be object storage somewhere, fetching them, basically giving them directly into the serving engine, so the serving engine itself can load them as local files into memory and then serve them. So what does that actually mean? So what do we need to have in the model repository in order for the model repository to provide all these different interfaces for the model provisioning sidecar to actually in real time configure the serving engine itself, right? That's kind of the goal, to in runtime configure the serving engine in a way that is hand over hand. No need to take down the service in order to upgrade, no need to take down the service when we change something. It should all be transparent. At the end of the day, this is production design. We want to make sure that everything can always be up and running there. So from the model repository perspective, we need to make sure that we have a model entity, right? So that we can query a unique ID that represents that model. We have to have versioning of a sort. So versioning is whatever you feel fits best to your specific use cases. It can be semantic versioning, can be used with tagging, key value. It doesn't really matter as long as this is consistent along the entire end-to-end workflow. So from actually developing the models themselves to application level, later using them, we have to understand which model is being used where. So this versioning system needs to be very consistent. Then we have states. So think about states as different states of the model being deployed. So maybe it's A/B testing, canary deployment, old or deprecated. These states, again, can be stored as tags on top of the models, but the idea is that it's very clear from a user's perspective. A new user coming into the system, they should be able to fully understand what's being deployed and how it's being used. That's why it's so important. And then at the end, we have events. Events are, think of it as the ability to actually trigger something in the system and when we have a change. So if we think about the model provisioning, at the end, what it can do is it can pull the state of the entire model repository, and when there is a change, it needs to be able to understand what that change is. So a new model being provisioned or deployed, published, and it needs to fetch the data and configure in real time the serving engine itself. So that's kind of events from this perspective. Then obviously we have to have API access, otherwise nothing is working. And lastly, we have to have permissions, right? So we have user or credentials that are for read access. For example, the model provisioning is only reading the state, it's never changing. Then we have a different entity, which we'll touch in a second, think automation, etc. It needs the ability to actually create a new version, set up a tag, and deploy based on those different events. Okay, so we touched that aspect of automation, right? We touched that aspect of, okay, so we need to have an API, but let's think of it from a more of a software development perspective. At the end, we need to get to a point where model deployment is as a part of the CI/CD process, and it should be able to use the same tools that we already love and use, right? So if we think about Git Actions or Jenkins, or actually integrate that into the entire experiment management solution that we're using. So when I say experiment management, I mean the process where we actually train new models, connect the code with a trained model and the data, etc. Obviously, this is a must in order to debug performance, but we might also want to combine this entire process and streamline it so we have full visibility from training the models, data, code, etc., parameters, to actually the endpoint that deploys that specific model, right? So in order for us to connect with these three different services, we must provide a specific API, right? So to publish a model, to change a state or a tag of a model, to delete a model, or decommission a model. These APIs allow us to actually automate this process, right? So from a process where every time we had a new model, we had to create a new container, push it into the container registry, deploy it manually, meaning access to the Kubernetes cluster, etc. So from a DevOps perspective, with this capability, with this ability to abstract everything, create an API for a change inside the model repository, and then an entire workflow that takes that change and deploys it, that means that we get to a place where everything can be automated. And if you think about it, no credentials need to be passed throughout this entire process. So actually deploying a new model does not imply having access to our entire Kubernetes cluster. And that's actually what we want. We want to separate the interface of deploying something from managing the cluster itself. And this is important for scale because when we think about automation, we cannot have credentials kind of flying around with too many users. We want them tied with orchestrating or provisioning the resources, not with orchestrating new models and deploying new endpoints. So continuous deployment. What it actually means, as we just discussed, is having that ability to have an API that allows us to deploy this entire thing from code. And meaning deploying it from code, meaning, again, Git actions, Jenkins, etc., without access to the Kubernetes cluster. It sounds trivial. It is not trivial. Having this entire end-to-end solution means that really, once we set up this entire infrastructure, it means that this basically means maintenance only. And that means that any new model, any new endpoint is totally transparent. There is no need to go back and change the cluster. That means that the cluster itself maintains full elasticity based on the load of the system and not based on the development and the need for deploying new models and upgrading the upgrade process itself. And this is huge. It means that we have time to put into making our cluster more efficient in terms of costs and scalability, rather than constantly chasing our tail and releasing new models and spending time on that, because we now have a system that actually automates this entire thing, right? So let's assume that we have that system. The next challenge is obviously monitoring the system, right? So if before this entire process was quite manual, because we had to, again, build a container per endpoint, package the entire thing, deploy it. Now that we have an API that does that, and let's assume that we also connected it with our Git actions, now we have to create a dashboard so we know what we have deployed in production and sort of collect statistics so we better understand the performance of those models. Those models are important for us because now when we have this automation, we first have to understand how the models are being used and the performance of the cluster. So things like the most basic stuff, latency, how much time it takes us to actually answer a request, right? That actually connects to the load on the entire system. That gives us feedback on the auto-scaling, just making sure that the latency is always under a specific threshold. That means that we can actually use it. And that implies that if we have high load on the system actually auto-scales transparently, and that actually works. The second thing is understanding how the models are being used. And that's a lot easier said than done, right? Understanding how models are being used, think of it this way, right? So we have a model predicting something. And let's assume that that model at the end that needs to get the input from several columns. Imagine a table, different columns, different features. The application might have a bug, so it will replace the order. That obviously will affect the result of the model itself. Or maybe the model itself did not expect specific set of parameters, right? Like an age out of scope or location out of scope. Things that we never actually thought about when we trained the model, but in reality, we are getting that specific type of data, and that might throw away the model performance, right? In order to actually detect them, and there is no performance metric, right? We do not know what the correct answer is, right? We predict something. It doesn't mean that we know what the correct answer is. So we don't have the ground truth, so we cannot output the accuracy of the model. The only thing that we have is a distribution of the input. So if we have to add something to the system other than the obvious, okay, this is what's being deployed and that's a latency and that's a load, these are insights into what the model is getting. Again, going back to the example of different columns, different data. So what's the distribution of that data? Understanding if this is out of distribution sampling, if this is consistent, etc. And then on the other end of things, what the model actually predicted, right? So if the model is constantly predicting the same result, so for example, within classification, it will always say everything is a cat. We want to somehow visualize that. So at least we have a dashboard that presents the distribution of different classes or a distribution of a continuous value, and then pushing that into a histogram over time. Again, trying to check whether we have something that is inconsistent of what we had. in order to actually increase this visibility, we have to build a process that, alongside serving the model, it also collects statistics. Those statistics we push into a dashboard, and that actually increases the visibility of the model deployed inside our system, right? So let's revisit the design. And now let's add another layer that is basically in parallel to the serving itself. We add another layer that is the statistics layer, right? So let's take the pre and post processing container as the center of this entire thing. Basically, it holds all the information that we need. It holds the inputs because it's actually exposing the external endpoint. It holds the output, again, storing the result of the model. Even though the model was inferred by another container, it actually stores the results, post-processing included. It stores the latency itself, because most of the latency will be coming from the inference itself. So it has the statistics on the inference latency, basically waiting for the inference, the serving engine to return the result. And we want to package this entire information. We have to think about what exactly are we packaging. We do not want to overload the system. And then we want to ship it into a statistics collection container. So let's assume that we have Kafka here doing the shipping for us, because at the end we do not want to worry about this shipping. It happens in parallel to the serving, and obviously the first item here is making sure that we can still serve the request very quickly. So in parallel, we have to ship the statistics. We will be using Kafka here in order to do the shipping itself. But then, even though in theory we can just push the entire thing into some time series database, we want to allow the flexibility of adding another layer of pre-processing for these statistics. So for example, just understanding the different types of maybe headers or arguments or information that is coming from the request itself. So the idea here is to allow the data scientists to have a piece of code that hopefully comes alongside the model that takes some information based on the pre-processing and post-processing information that we have and create statistics over it. So let's think very simple use case, just creating a histogram over the output data, output numbers, like histogram over time, and then another histogram of the different fields that are used in terms of the prediction. So think like whether we're using all the different fields or all the different columns, or maybe the distribution of a value within the column. That specific information needs to be processed in the statistics collection container. And obviously this is running on a totally different node. The idea here is we are dividing the load of creating the visibility layer, the statistics layer, from actually serving the model itself. This is important. We do not want to create another delay in the serving service itself on the one hand, but on the other hand, this is very important. And we cannot assume that we will be able to do everything once the data is being pushed into the time series database, because at the end, we're constantly reporting. This is why I'm referring it to a time series database. We're constantly reporting something. So it's a time series on the one hand, but on the other hand, we cannot expect to have all the capabilities. And we want that dashboard to be as transparent as possible. We do not want to have that post-processing done in the background. We want as much real-time as possible in terms of alerts and dashboard actually representing what's going on live on our deployment production cluster. So let's dive into what is this statistics collection container, right? So the statistics collection container is basically a container running some piece of code that takes the statistics coming directly from the pre and post processing container, and then process it in a way that we can push it into a time series database. The reason, again, for time series database is because we're constantly providing new information. So again, going back into the simple use case, think like a sliding window with a histogram, where we constantly compute the histogram over a time frame, let's say a couple of minutes. Once we have the histogram itself, we push it. Why we want to do that, and instead of just pushing the entire thing into the time series database? First of all, just think about the load on the system. So thousands and millions of requests per minute. There is no reason to push them into the time series database. We will never use them, and we do not need that fine granularity in terms of data. That said, we still want to have that statistics. This is exactly why we have this container actually summarizing the load on a specific model and the performance of a specific model. But this still is based on time. So for example, rush hour, day of the week, etc. So this is still time series because it will be changing, right? And that capability needs to be part of the statistics collection container, actually chewing, if you will, some of the data in a manner that pre-process it so that later we can have an easy time presenting the data, visualizing it, and creating alerts. So specifically, we can think of the time series data, like think Prometheus, for example. Then we have Grafana as an entity that does dashboarding. Any entity will suffice, but the idea is that it has to be flexible. So it's so again, from a more holistic approach, we are deploying multiple models constantly here. We have to make sure that we have that flexibility of refining the dashboard, refining the metrics that we're looking into. So we have an updated view of what's going on in the cluster, right? If this is not the case, that means that every model that we're deploying, we need to deploy another dashboard, and we don't want that. We want that the dashboarding solution that we have to be flexible enough to present the data. And this is why it's important that the model itself will, if you will, take some responsibility on the statistics that it's providing. So from the dashboard perspective, it should be as transparent as possible, but from the model perspective, all the knowledge of what's important, what's not, is over there, so we have to couple it. So think about it as a pre- and post-processing code, but also some statistics gathering code that comes along with the model itself, right? And that the statistics collection container is actually running for us. So we have the dashboard. Then on top of it, we have alerts. So think about alerts from, for example, Grafana perspective. That's basically saying, okay, if a value is above or below a threshold, create an alert, shoot us an email, Slack, whatever. But the idea here is by that time that we have it in Grafana, we have a single value that represents the most informative part of the model. So a very good intuition would be, for example, latency, right? So if the latency goes about a specific threshold, which makes it unusable, fire an alert, we have something wrong with the cluster, it's not auto-scaling as we predicted, etc. Another alert could be if there is a difference between the two different histograms, so things like difference between two different vectors. If this is too large, meaning something happened in the distribution of the data, whether this is the input or the output, it doesn't matter. This is something that we want to make sure that we get an alert so we can take a look at. So very simple things, but very valuable and powerful in terms of managing this entire cluster. Again, thinking about scale, multiple models, we have to have them, otherwise we will not be able to track everything that's going on. So we managed to have those alerts just because we kind of pre-process the statistics in a way that allows us to very simply create those. So the parameters that we're actually sending and then Grafana is actually presenting are the parameters or the matrices that actually represent the performance of the model. Again, a drift over time in terms of a change in histogram, latency, etc. And that allows us that gives us the capability of first displaying it, but again, secondly, create alerts so we constantly have insights into what's going on in the model serving cluster itself. So if we think about those, we also can think about, okay, so let's think some more complicated things, right? So if those were relatively simple stuff, again, thresholds over latency, etc., we can think about more sophisticated machine learning driven drift detection. So again, changes in histograms or in distribution. So whether this distribution is continuous or discrete, so KL or KS tests. Online learning, maybe trying to predict what is going to happen in terms of the performance of a model based on time of day, the day of the week, etc. And lastly, maybe taking this entire thing and just fitting it into a model drift as a service, right? taking the metadata information, for example, type of day, geolocation, things that the model is not actually using, but might imply the performance of a model as we think about from more of a holistic approach, right? Load on the system based on time of day, rush hour, etc. And push that into more of a model drift service that does that for us. Again, doing another level of complexity in terms of predicting whether the model is ill behaving, because at the end, the only goal of this statistics collection is to actually detect if the model is performing as we predicted. Right? That's kind of the goal here, is not only to create visibility but also create automation in terms of understanding performance per model. So with that, I think that we can summarize what we covered here today, and that was a lot. So let's start small. I guess this is the main idea. Start with something that is easily implemented, can scale at least up to a point, and brings value into your process. If we're aiming too high, that means that we will be spending time building something that is generic without getting feedback from the applications, from the production, from actually using those models. And it's important to think iteratively, because at the end, we want to build something that is customized and works for our specific use case. There is no one size fits all in terms of the entire thing. It's at the end, we will have to have points where we want to customize, and this is important. The second is always think about visibility. So holistically, models being served, performance per model, integrating that into the process of actually developing new models, right? So experiment management, orchestration, automation of, we haven't touched it, but obviously triggering model retraining based on model drift, etc. This entire thing needs to have a more of a holistic perspective, and it's important to keep that in mind, because at the end it will affect the way that you construct your own specific design on top of it. Then it's important to also understand, and it sounds like a nuance, but it is not, that serving service and inference scaling is not the same thing, right? So inference scaling, it's basically the serving engine capabilities, which these days we can actually get out of the box. Again, NVIDIA Trend, for example, Torch Serve, TF Serving, they all provide that. But in order to actually get that to a level where you build solutions on top of it, you have to have an entire architecture on top of it. And that architecture that we just discussed today is the serving service architecture. And this is not the same as just running the model in inference mode. There's a lot more things that we have to take into account in order to actually build something that scales. And lastly, efficiency actually matters. At the end of the day, this cluster will cost money. And we want to make sure that we deploy it and use it in a way that is most efficient as possible. So we do not have idle nodes, that we use hardware the best way possible, meaning for the correct task, that we have fine enough granularity that we can split tasks into the most cost-effective resources that we have in the cluster. And obviously we want to have transparent scalability, right? So if we have high load, we provision more nodes. If the load decreases, we release them, and we build something that is as efficient as possible, but at the same time totally transparent. So we do not have to constantly manually upgrade and downgrade our instances. So if everything that I just described is of interest to you, if you think that this might be a good match for what you're thinking about building, check out ClearML Serving. It basically implements everything that we just discussed. It's fully open source. You can build on top of it. It relies on all the different points that we just covered. Obviously scales, and it's a very holistic solution that allows you guys to build and customize your own serving service on top of it. So go check it out. Any questions? Now will be a good time. If for some reason we do not cover it, you can find us on our Slack channel. Go check out the website or the GitHub for links and issues. And I guess thank you for joining.